Okay, greetings, colleagues and friends. My name is Washington Ochieng. I'm the current head of the Department of Civil and Environmental Engineering here at Imperial College London. I am delighted to welcome you all in person and virtually to Imperial College London and our department. So I've just been thinking, what can I say about Professor Wouter Buytaert? So let me start by saying that he grew up in the Flemish part of Belgium. He studied bioscience engineering at the Catholic University of Leuven in Belgium. He had the opportunity to travel to Ecuador for 4 months as part of his final year research project, studying the impact of land use on the hydrological processes of high mountain, wetland, and grassland ecosystems. Wouter graduated with maximum cum laude. He was first of a class, or in a class of 180 students. Wouter then stayed in Leuven to embark upon a Doctor of Philosophy on the same topic as his research project, supervised by Professor Sepe Dekkers and Guido Weisur. He did extensive fieldwork in Ecuador during that period. He obtained his PhD in 2004 and continued 1 year as a postdoctoral researcher in the same group. He kept going. He obtained a European Marie Curie Fellowship to work with the research group of Professor Keith Bevan at Lancaster University, finishing that in 2007. He then moved to the University of Bristol in October 2007 to take up an RC UK Fellowship in Risk and Uncertainty, but then decided to move to Imperial College in 2009 to work with Professor Wouter Buytaert. Wouter became a lecturer in 2011, senior lecturer in 2014, reader in 2017, and finally professor of hydrology and water resources in 2020. So over the last decade, he has built a successful and dynamic research group through which more than 20 PhD students, 11 postdoctoral researchers, and numerous MSc and MH students have passed. He currently manages a large portfolio of research projects focused on water resources and environmental change. He is a clear ambassador of the college's renowned reputation as a global university with projects and collaborations all over the world, from Peru through the United Kingdom to the Philippines. Wouter was recently awarded the prestigious Darcy Medal of the European Geosciences Union for outstanding scientific contributions in water resources research and water resources engineering and management. So it is at this point, having read all of that, I invite Professor Wouter Buytaert, please step up and deliver your inaugural lecture.
Thank you, Washington. Good morning, good afternoon, good evening, perhaps good night, depending on where you dial in from. Indeed, it's my honor to give this lecture to a great audience here in person, but also, hopefully, a large audience online. That's perhaps one of the main advantages of the pandemic, that we really managed to organize global events and allow people to come in from all over the world. So thank you very much, Washington. It's a great pleasure to give today my inaugural lecture, taking you on a virtual journey throughout the world in pursuit of this concept of global water security. But before I do so, I would like to do a little experiment for which I'll need an assistant. Would someone be willing to come and help me with a quick experiment? Thank you very much. Give a round of applause. It's quite straightforward. All I need you to do is read out the number that is there on the scale that gives us the the mass of this banana plant together with the soil and the pot it's standing in. So if you can please do that, I'll note it down on the whiteboard.
19033.
And that's grams. Thank you very much. Give a round of applause. Good. Back to the lecture. I promised to take you on a journey through the world, and we'll start in the Andes. As most of you, or many of you, will know, or as Washington indeed just mentioned, the place where my own scientific career started as an MSc student in Ecuador. But here I take you to Peru, very close, a view over the Andes, the largest mountain range in the world, from the very southern tip of the South American continent, all along the Pacific Ocean, over to Central America, and even further north into the US and Canada. A very diverse and complex system, both from a human perspective, lots of different ancient and modern cultures and societies, but also very complex from a natural environment. Very diverse climate patterns, some of the wettest and the driest places on Earth, a complex vegetation, soils, geology, and sometimes also quite a harsh place, especially up in the mountains, cold climates, cold nights, long dry seasons. So quite a challenge for people to make a living in that kind of environment. Indeed, especially in the Altiplano, as you can see here, vast highlands, as they're called, consisting of grasslands, wetlands, and forests and other ecosystems, intercepted by those deep and steep valleys where people try and cultivate steep slopes prone to erosion, prone to runoff. So a difficult environment where people really rely a lot on the ecosystem services that the surrounding environment provides, including one of which is, of course, water, fundamental to all life and particularly pronounced in those regions. So people use water for things like agriculture, for human consumption, for industries. So people are also exposed to episodes when there's not enough water, indeed long dry seasons which might evolve into drought periods. But also potentially people might be exposed to too much water. Heavy tropical thunderstorms and rainfall events might create episodes of flooding, as you can see here, for instance, the Vilcanota River close to the famous archaeological site of Machu Picchu. So a good example, a good illustration of this concept of water security, which is a cornerstone of sustainable development, the fact that we try and capture the fact that we all rely on water of sufficient quantity and quality to live the life we value, but that we're also exposed to risks related to water. And that's really what we try to contribute to as a research group. I'm a hydrologist and water resources engineer, as my title mentions, and we try to contribute to that much broader concept of water security. Indeed, you can call that and one of the wicked problems that society is trying to solve, in the sense that water security is very multidimensional, depends on natural processes, but also human processes, a lot of different activities that interact, that feedback, and that all together determine whether a person living in a certain location is water secure or what's the level of water security. And what do scientists do when they come across a very complex, wicked problem, or try and develop a framework to make sense and try and pick it apart into smaller, more easily digestible problems? And that's what I'm going to do, give you a bit of the theoretical framework. It's a scientific lecture, after all, to guide you and to show where the position of a hydrologist and water resources engineer is within that much broader context of water security. And there's different ways of entry or looking at the concept of water security. But one way of doing it is by looking at water as a risk. Too little, try and avoid that we have too little or too much. And risk is a concept that's often dealt with in natural science, particularly in relation to natural hazards, including the IPCC, for instance. You might remember last week the publication of the latest 6th IPCC assessment report, unfortunately a bit snowed under by the other awful news that's happening in the world at the moment. But so the IPCC, for instance, looks at risk, in that case climate risk, and defines it as a combination of the natural hazards, the physical process that happens, for instance, a flood, but also the exposure of people to that flood, as well as their capacity to deal with their resilience towards that flood. And so, for instance, in the context of water, take, for instance, water shortage, then that water shortage really is the combination of those three processes. And as hydrologists, we particularly look at water shortage as being essentially a function of both water supply, how much water is available, but also water demand, how much water is needed. There are places in the world that don't have much water, deserts, for instance, but that don't really have a problem with that, given that there's not many people needing or relying upon that water. So the water shortage, the physical component of that risk, can be segregated out into a combination of demand and supply. And again, as a hydrologist, we're particularly interested in understanding that supply. And if we pick that again apart, then we will typically see that in a landscape, such as the river basin you can see here, that very different hydrological processes work together to determine the total amount of water available, for instance, in a river in a certain part of the landscape. Using here an example of, for instance, a mountainous catchment, if you go to the very top, then a lot of water comes from what we call the cryosphere, snow, ice, glaciers, but the further down you go, other processes take over and become more prominent. Wetlands, for instance, subsurface storage in hill slopes in the hilly parts, up to potentially very large subsurface aquifers of the type that, for instance, my colleague Adrian Butler is looking at in more detail. So that is the little role that hydrologists play, try and understand those processes and how they cascade through to inform or to determine the broader context of water security. So what do we do? Well, first of all, we need to understand the hydrology. If we are to make informed decisions, if we try to get to grips with that water availability, then ideally, really, we should try to get to grips with all the different processes, the flows and stores of water through that landscape. From very fast surface flows on the steep hill slopes, water that after it rains get into the river very quickly, create peak flows, to the very slow stores of subsurface storage and migration that can take many, many days or even many months to get into the river. And obviously they will contribute in different moments and in different locations to that dynamic process of river flow, as you know, is very variable in space and time. And those processes are governed by the different ecosystems and the different processes as they happen in the vegetation, so the weather patterns, obviously, as well, vegetation, soils, and you can imagine that, for instance, a grassland ecosystem, as here on top, will react and behave hydrologically in very different ways than, for instance, a lush mountain cloud forest, as you can see here at the bottom. And the main problem with doing that, with getting to grips with those processes, is that for the large part of the world, we count on very few data, quantitative information about those processes. Indeed, most of the world is hydrologically what we would call data scarce. There's very little quantitative observations, data on those different processes. So getting to grips with those requires something is wrong. Let's try and get that solved. Here we are. No, that's a bit strange. Technology. We're back. Not yet, sorry. I'll take perhaps the next one and see whether that's... There we are. Thanks, Tom. That should work. Thank you very much. After a little intermezzo, hey, we're back. I'm sure you can cut it out on the recording afterwards. So, data, the lack of data. And that takes me back to the very start of my research career, where one of the first challenges I had to overcome when studying the grassland, the mountain grassland ecosystem, as you can see there, which is one of the main natural water towers for much of the tropical Andes, but where I was faced with a lack of data, a lack of quantitative information to start doing analyses. So I had to figure out how to build a V-notch weir, which is the type of structure that hydrologists use to measure river flow, to start collecting those data. And this is probably not the most professional V-notch weir that you'll ever seen in your career, but it did the job and allowed me to implement some experiments. And the type of experiments that we implemented was work, by the way, that I did when working with the PROMAS research team at the University of Cuenca in Ecuador, was try and compare some different catchments to assess the impact of human activities, particularly land use, such as cultivation and pine forestation, on the hydrological response. And so we collected those data, analyzed them, and actually found that, for instance, pine plantations consume a lot of water, evaporate it, transpire it, and as a result, it's not available anymore to run off in the stream. So that's quite a big impact on stream flow, as the hydrologists will be able to gauge here on the flow duration curve, which is a typical way which summarize the impact of plant use on both peak flows here on the left-hand side and base flows, which are important for water supply. So we did that experiment and actually gathered quite some useful information, but a single catchment or a single experiment obviously doesn't say too much. One swallow doesn't make summer, as they say. With a single experiment, you can't extrapolate, you can't say much at the regional scale, especially not for an environment as diverse and complex as the Andes. The best way to solve that is by doing more experiments, but it took me pretty much an entire PhD to set up one or two of those comparisons, so you can imagine how much effort it is to repeat that over an area the size of the Andes. But I was lucky enough then to team up with a team led by the fellow hydrologist Bert de Bièvre, who was at the NGO Condesan at that moment, leading a research and development project called Proyecto Páramo Andino, where they had good interactions and good contacts with NGOs and universities and communities with similar interests, and they were able to set up what you could call a community of practice, a group of people with the same interest, understanding the hydrology of Andean ecosystems and the impact of land use change thereon. And obviously, sharing the work makes it much easier, so we started setting up different experiments all over the Andes. And that started more than 10 years ago, and now the network has grown with well more than 100 members managing, I think, around 59 sites or 59 catchments in 22 sites all over the Andes, from Venezuela in the north down to Chile and in between. And that was a great joint effort to extend that evidence base on the hydrological processes, as well as the impact of different types of land management, cultivation, livestock, forestation. And that obviously allowed us to draw much more firm and robust conclusions about how those ecosystems behave and how management can alter them. And I won't go into too much detail. For the hydrologists or anyone who's interested, you can read up the excellent paper by Boris Ochoa Tokachi, who analyzed this data set as part of his PhD in our group. So that's great, but obviously as scientists, we're always interested in seeing how we can improve that process and do even better. And so there are a couple of entry points, or a couple of ways we try to improve and go beyond and extend that activity. And one of the bottlenecks we came across was the lack of, or the fact that the instruments we used were still quite expensive, quite prone to damage, quite difficult to operate in those quite remote and harsh environments where we implemented them. Here you see, for instance, Junior, one of the EMEA technicians, doing a great job with dealing with one of the rain gauges. And as a research group, and particularly as engineers, that was definitely a challenge we were keen to take up. And so we tried and explored, especially riding on the wave of what is called open hardware, Arduino, Raspberry Pi, and similar technologies, and see whether we could use that technology to build sensors that are cheaper, more robust, and more user-friendly to use in those environments. And we managed to do so with good success. Those new sensors we built, as you can see here, for instance, are used within EMEA, for instance, the Bolivian site most recently, but also allowed us to explore their use in different contexts. For instance, in that other great mountain range in the world, the Himalayas, which deals with very similar problems of water scarcity and flooding, and also deals with the lack of data. So we used and developed, for instance, new technologies, in this case based on laser sensors, to measure river flow in the great Himalayan rivers and integrate them, explore the use of that technology in the context of flood resilience building and community-based early warning, flood early warning in India and Nepal, together with collaborators of, for instance, Practical Action, local universities like IIT, Roorkee, Tribhuvan University in Nepal, as well as more local ones here, like the University of Birmingham. And people like Johnny Paul and Neeraj Shah in the group have made great contributions to developing and testing those sensors. Or more recently, the work of Will Van Ness in our research group, PhD student, who looks at exploring those technologies in the context of drought early warning in the Horn of Africa, another region that is extremely exposed to drought risk and also counts with very few data. So great opportunities there to think about how to leverage new technologies to generate more data, kind of the bread and butter of the kind of quantitative analysis that helps supporting drought and flood resilience. But data can only look back. We can only measure what we see at the moment, look back to historic data, but data don't help us with looking into the future. By very definition, we can't measure the future. We only can make predictions and try and use the past to make predictions about the future. And obviously that's what a catchment manager wants to do, not just to know what happened after you deforested the catchment, but actually thinking about whether it's relevant or what kind of activities can be implemented to increase water availability or protect against peak flows in the future. The kind of what-if questions, as they're known in policy, what if we allow farmers to cultivate a landscape and obviously make a local living? That's obviously great for local development, but might potentially have negative side effects downstream. So a policymaker really tries to balance out those different interests and decide what's best in the grand scheme of things. And so questions like, what if agriculture expands within mountains? What if pine trees are being built? Will they consume too much water and create drought or increased drought risk downstream? What with increasing urbanization, what does that mean in terms of water supply, but also demand? Or the big elephant in the room, how will climate change, for instance, change water availability, peak flows, and base flows in the future? We can't measure those things directly, so instead we use models, basically computational representations of our system, to make those predictions and to run scenarios about potential future change. And so another big activity within the research group is building those models, testing them, and making them apt for scenario analysis. And here's, for instance, an example of a model representing those wetlands that I mentioned earlier and trying to represent all the different types of processes, evaporation and transpiration, water consumption of the vegetation, infiltration of water into the soils, storage and water flow in the subsurface, bring them all together in our computational model that allows us to run scenarios and make predictions about the future. Here, for instance, a model that Anthony within our team is working on. But also going beyond just the hydrology, I started off with showing you how hydrology is a piece of a puzzle, of a much bigger puzzle towards water security. So we've also tried to bring in some of those other components. Here, for instance, a model that Jimmy O'Keefe, another PhD student, has built to incorporate also the human component. In this particular case, how farmers in India make decisions about the type of and the source of water to use for irrigation, because they can often choose between using groundwater, which might deplete subsurface aquifers, versus surface water, which is often less reliable. So to get to grips with the way that people use water and therefore alter the flows of water through the landscape, you need to add that human component as well. Or the work of Clara Jimeno in our group, looking at the catchment as a whole system, using the expertise of my esteemed colleague Anna Mage on systems analysis, trying to look at the different ways that people make use of the water cycle, directly water for consumption, but also indirectly through the other ecosystem services, such as agriculture, biodiversity, ecosystem preservation, which all contribute somehow to the quality of life that people experience in different parts of the catchment. So here, a systems model that tries to get to grips with that complexity and the upstream, downstream linkages in the catchment that provides water to the city of Lima in Peru. So models, a very important aspect of making predictions and evaluate scenarios that can help with making better decisions on catchment management. So data and models are very useful, very good tools, but obviously someone needs to use them. So the third ingredient in sustainable catchment management is the people. And over the last few years, we've had the opportunity of exploring a bit more how people enter that picture and how they interact with hydrological knowledge and how hydrological knowledge is being created to support decision-making on water. And we're in good company because that's also an aspect that's very high on policymakers' agenda. They look, for instance, at the UN Sustainable Development Goals, which has this goal 17, which is all about partnerships, interaction, and collaboration between science, but also governments, industry, the third sector, local communities, really as a way to enhance the participation and the way that knowledge is being created to support sustainable development. And there are many reasons why participation is good, but just to give you a few examples. So for instance, if you want to make sure that the information and the knowledge that you create is relevant for a problem at hand, obviously you need to involve the end users in the problem identification. What are the bottlenecks? What is really the type of knowledge that can support making local decisions about, for instance, water availability, ecosystem management? But also knowledge integration. Obviously scientists produce knowledge, that's their job, but they don't have a monopoly on creating knowledge. And indeed, especially in the context of water, local people often already know an awful lot about how water moves through the landscape, where water is, what are the dynamics. And so using that local knowledge and integrating that in the more formal scientific knowledge is increasingly important, and recognize that we really need to be able to do that to maximize, again, the knowledge base for decision making. And even in the data collection, you might be familiar with the concept of citizen science, also very, very high on the policymakers' minds as a way to include people not just in using the knowledge, but really also in the nitty-gritty of the scientific discovery process, collecting data with low cost and easy-to-use sensors, interpreting data. So involving people throughout the whole chain can make of data and knowledge creation is increasingly important. And so over the last few years, we've had the opportunity to team up with some great social scientists like Art, Julian, Timos, and others to look a bit more broadly at a catchment and how knowledge is being created and how we can involve and make each aspect of what we call the knowledge creation process as participatory and inclusive as possible, using low-cost sensors, for instance, to allow people to collect data in the context of participatory flood forecasting, but also using ICT tools for people to access the data and explore and extract knowledge themselves. And the way we've done that was very much through this concept of environmental virtual observatories, which was pitched by the UK Natural Environment Council about 10 years ago as a way to explore how new technologies can play a role in making each of those steps in the knowledge creation process more participatory. Again, from the sensors themselves, and as much as we use the sensors we build to collect data, we also try and use them as a way to incorporate and incorporate local people and make that process more participatory, to the use of ICT tools like tablets to give people better access to information, and also to comment and interact and give their own opinion about what they see and how they experience their environment. So we've been able to really do some great work thanks to the help of a lot of people, including Zed, who's somewhere in the room, has done some great work on embarking upon that interdisciplinary challenge of exploring and integrating different knowledge bases within the context of water resources management in places like Peru, Nepal, Kyrgyzstan, and others. And really the end goal of doing that is to come towards something that UNESCO calls open science, basically make the science as accessible, as open, and as useful as possible for the whole of humankind. And here we should shout out to UNESCO, and especially the International or Intergovernmental Hydrology Program, with which we've been working for, I think, more than a decade now, and had the opportunity to contribute to policy briefs and publications that, again, enable or facilitate knowledge transfer and uptake of knowledge in a policy context. Well, not just publications, also, for instance, in the group, we try to put a lot of effort in documenting, for instance, the use of the sensors, making all the blueprints and the code available, creating videos, doing online training and interactive workshops to, again, involve people and providing the opportunity to participate in the process of data collection, analysis, and interpretation. So now to go back to the Andes, how are all these concepts and tools and grand ideas actually being used? Well, to go back to the Andes, I mentioned that it's a system under severe pressure where water security is really very high on the minds of local policymakers. And obviously they've been doing that for a long time, building infrastructure like dams, reservoirs, canals, to store the water and to ensure that small communities all the way to big cities do have better access to water. And that has worked really well and has enhanced living standards over the last decades tremendously. But those solutions also have a couple of problems. They tend to be quite large and expensive. Building a dam is something you need sufficient resources for. But they're also not very flexible in the sense that if, for instance, rainfall amounts change under the context of climate change, then your dam might actually not be able to fill up anymore, or might be too small, or maybe too large. And so you can't really adapt to changing environments, changing boundary conditions. And so for that reason, policymakers have really been exploring new types of managing water, new tools in the toolbox of the water resources manager, if you will, to see whether they can make that whole process of water management more flexible, more adaptive, cheaper, and more future-proof when boundary conditions change. Some examples, for instance, are protecting the upland areas to make sure that the water they provide is of good quality, soil conservation to enhance the infiltration of water in aquifers where it can be stored and extracted much more easily than when it runs off very quickly in the river, to even local surface storage as well as artificial recharge, forcing water to infiltrate and replenish the groundwater reservoirs. So these are novel or newer types of managing the landscape, which are often put under the header of nature-based solutions, because a common characteristic is that they apply or they leverage natural processes much more than the classic concrete-based storage mechanisms and solutions. But the main problem of doing that is that many of those processes are not as well known as the classic solutions. If you reforest a catchment, then you can expect that you have more recharge, more infiltration, but it's very hard to quantify. And so the main bottleneck is really having that quantitative evidence to build it into an engineering solution. And so one example of the type of solutions that policymakers were looking at is part of what is called sowing and harvesting, a local practice that has been going on for centuries, almost a kind of ancient practice, where people built local small canals that diverted water from a little mountain stream, as you can see here, and dumped it onto the hill slope, where it's allowed to infiltrate, migrate, and support and replenish reservoirs further downstream. And so a solution that drew a lot of interest, but where a lack of scientific information really was or prevented the further exploration in the context of water engineering. And the team of Condé Nast, which I mentioned earlier, had, for that reason, did an experiment with a fluorescent tracer, as you can see here, to quantify the duration and the residence time of the water in that hill slope, and actually see when exactly it resurfaces and how it's, and to which extent it can replenish base flows during the dry season. And so then we took those results from that experiment and built a model. This work that's led by Boris as part of his PhD, and we built a model to actually evaluate whether such a system, if expanded and upscaled to the whole catchment, could effectively contribute to base flow, river flow during the dry season, which is when it's most critical for water supply for instance, the city of Lima that sits at the foot of the Andean mountains. And we found that effectively those nature-based solutions, that artificial recharge, can help increasing base flow, but as you can see, not through the whole dry period. So it definitely cannot replace the artificial storage which is already in place, which you can see here with the red line of river flow. But it can enhance and actually make that classic infrastructure more effective and allowing it to do more, for instance, on the future conditions of change. And so a good example of how a combination of classic and new approaches is probably the most flexible way to enhance the system towards the future while still keeping some options open without needing, for instance, to build a major new reservoir in the future. And that's really the whole purpose of the approach, is to try and find, depending on the local setting, depending on the different options, the different tools in the toolbox, from classic infrastructure like reservoirs and flood defenses, and also some of those new approaches, and try and gather the evidence, the scientific evidence that allows to build and to come up with the best combination of approaches within a certain environmental and social context. And that's, for instance, what's happening in the river basin of the city of Quito, where the government of Peru is experimenting with new ways, what they call sharing the benefits of ecosystem services, setting up a water fund in which the water consumers of Lima pay into, and which is then used to restore and to invest in watershed interventions that benefit both the upstream and downstream populations. And that's work that's led by SUNAS, the Water Regulation Agency, a team of people with which we've been working also for a very, very long time, and where that interaction between science and policy has really allowed us to focus and to generate new science that directly feeds into better local water resources management. Good, and that's all I wanted to say, but before we finish, we need to continue our experiment, so if my little helper would be willing to come back and read out the scale again, then we can finish off our experiment. So if you can tell me.
19027.
Thank you very much. Give him a round of applause, please. So our plant here has actually lost weight. Maybe it's on a diet, or maybe someone stole a banana, or maybe the plant has been growing, but instead it's been consuming water, and the reduction in weight might well be the amount of water that has been evaporated or transpired through the plant and escaped into the air. And indeed, 6 grams of water has escaped, and this is an experiment that is, as simple as it might be, quite common in hydrology and called a Lysometer Experiment as a way to quantify the water consumption of different types of plants. And that is very useful information. For instance, you can use that to calculate the crop coefficient of the Pema-Monteith equation, which you can then use to calculate the crop water requirements of, say, for instance, a banana plantation at the coast of Ecuador, at least if you make a couple of corrections and errors, because obviously the type of environment you've got here is quite different. So you might want to calculate the difference in temperature, the difference in radiation, not just the amount of radiation, but also the frequency, because fluorescent light here is obviously a very different wavelength than natural light. You need to correct for the incident angle of the solar radiation as well as the daylight time. And if you do all that, then you should get a result. And I expect that result in my mailbox tomorrow by 9 o'clock in the morning. If not, a late penalty will apply. Thank you very much.
Thank you very much, Professor Buytaert. The tradition normally is that we don't allow questions at inaugural lectures. That's the tradition. But given how close to home the topic has been, and given how excellent the presentation has been, Professor Wouter has, we decided to make an exception. Okay, so he's willing to take a few questions. And just using the prerogative of the chair, I've got one question just to kick it off. I mean, you mentioned this participatory data collection. And I was wondering how you validate that. You know, when people send data to you, they capture data, how do you validate that information?
That's a good question, and indeed one that is quite common, especially in the context of citizen science, and one of the main criticism, but they're not experts, how can you be sure that the data is of good quality? There are statistical ways to test that, and for instance, in our case, we have compared the data that come from the low-cost sensors as well as data and instruments managed by citizens with the classic scientific approaches and instruments, and actually found that very often the data is of very similar quality. Not always, but even there are ways to deal with that. You don't always need extremely high quality data, and obviously, and often there is actually more value, or at least as much value, in having more lower quality data than fewer high quality data. Obviously, that depends a lot on the specific type of question that you ask, but in many of the studies and the research that we do, having actually more data and covering a larger area, which, for instance, allows you to look at spatial patterns of precipitation, water availability in soils, etc. It gives more scientific value than having fewer and higher quality data. But it's obviously very, very context dependent, but we do have pretty robust ways to estimate the quality of citizen science or novel approaches to data collection to account for those issues.
Is this the same as crowdsourcing, or is it different?
Crowdsourcing is a type of citizen science that focuses particularly on the data collection aspect. Yeah, there's a lot of analogy.
Thank you. Any question, please, from the audience? Yes, Stephen. Professor Stephen Smith.
Yeah, as Wouter's head of section, I'm delighted to answer the next, to pose the next question.
Yes.
Wouter, you mentioned lots of different. People online.
So Professor Stephen Smith is our head of the Environment and Water Resources section in the department. Stephen.
Thank you, Wouter. Yeah, great talk. Thank you very much. Really enjoyed it. You mentioned lots of different mountain regions around the world. Do you find that the problems are similar in all of these regions, generally speaking? That's the part A. Part B, do you find if you've developed a model in one region, you can actually use it to predict behavior in another?
Yeah, very, very good question. A famous hydrologist once said, every catchment is unique, and that is definitely the case in mountain environments. So it's mostly a matter of making sure that you cover the range of processes as you can expect them. And that in a way is also an advantage of mountain environments. You have so much variability that you can actually, by choosing your catchments and locations right, you can capture a lot of that variability. And so you do have similar processes in different mountain environments, especially in relation to the natural processes, the way that water runs off, the way that snow melts, the ways that hill slopes behave. But where mountain regions obviously differ very significantly is in the human component, especially the social and cultural way that people make use of the landscape. I've got here a photo of Nepal, just to contrast Nepal with, for instance, Peru. The type of agriculture that is done in Nepal, because people eat far less meat, is much more focused on growing cereals, for instance, as you can see here from the photo. While in a mountain range like the Andes, you'll have much more livestock grazing. And so that obviously has implications both for the impact that people have on the environment. Cultivation uses and alters the hydrological processes in quite a different way than livestock does. But it also has an impact on the way that people use the water and the portfolio of ecosystem services, if you will, that they depend on.
Thank you. Let's check with Simon. Is any question online?
Yes, there is a question about the sensors. Professor Buytaert, can you say more about the type of sensors used to collect data? And do you use Internet of Things analytics on those data?
Yes, indeed. So we focused mostly on water level data in combination with those V-notch weirs that I showed earlier on, simply because river flow is one of the most fundamental type of measurements, and one where new technologies, particularly non-contact methods, have a lot of scope. So that's a specific technology that we focused on because it's what serves us as best. In terms of IoT, Internet of Things technologies, we do use some. We're starting to experiment with data transmission using local networks like LoRa and others. So we're eager adopters, but we remain water resources engineers, not electronic engineers, so very keen to stand on the shoulders of others, in this case the electronic engineers that develop those technologies, and then really what we try and do is leverage them for the specific purpose of alleviating the issue of data scarcity in mountains. So we're very eager users of the technology and crash test the technologies, if you will, in probably some of the most challenging environments that you can imagine.
Thank you. Back to the, yes, you, sir. The mic coming to you. If you'd like to say your name and affiliation, please.
Alejandro Dusayant from Universidad Aysén in Chile and Middlesex University. About a wonderful presentation. Maybe my only criticism is that there's no Chilean Andes. Maybe next one. As a ecology professor of mine and then colleague used to say, nature doesn't give without taking. There's a trade-off always. If you could comment on the natural flow regime and how, if at all, we need to be careful, cautious, whether with our nature-based solutions we might overshoot and maybe change the water resource in space or time in a way that might affect, for example, fluvial system species that depend on certain timing of water or quantity of water at certain time in the year.
Yeah, I think that's not unique, obviously, to nature-based solutions. Any intervention within the catchment hydrology will have an impact on, for instance, the downstream flow regime. Probably the biggest example is building a dam will clearly influence downstream bays and peak flows and the distribution. So any human activity that alters the catchment will have implications for things like ecological diversity and the ecological system. So I would put it broader, and I think there the key element is indeed ideally try and look at all the processes that are affected, and obviously very often a catchment is managed for a certain purpose, for instance, water supply of a downstream city, but any intervention will have that creates certain benefits is likely to create side effects, some of which might be disadvantages. I think that's the key reason to look at the catchment as a broader system with all the services that it provides to humanity, but also, for instance, in terms of ecology and ecological status, and getting to grips with those trade-offs and the total package of benefits and disbenefits, I think is key, and is very much where the discipline as a whole is trying to get to a more holistic understanding, if you will, rather than just looking at a specific process and tinkering with that, and potentially creating knock-on effects beyond your field of view, if you will. Yeah.
Thank you. So we go online, and then we go to Professor Buytaert after that. So Simon.
David, I think I would guess Hannah, says, nice talk, Wouter, congratulations. How do you ensure participants or citizens have the most useful science to make beneficial choices for their sustainable use of water resources and ecosystem services?
Good question from a long-term collaborator. He obviously knows where the biggest challenges lie in the science. Yeah, that really is one of the key challenges. So participation is all great, but coming to really an equitable relation between all the stakeholders is fundamental and is a big challenge. And in a way, I step a bit outside my area of expertise, but it's the reason why we try and include, for instance, social scientists who look at aspects like indeed access, but also, for instance, power relations. Because in the end, as a scientist, you're one of the actors, and at the same time, you try and take some distance from that whole process, and that's a bit of a walking and a thin line between different those different hats you've got, or the different roles that you play, and yeah, that's where we work together with social scientists that observe that process and try and understand to which extent that the new knowledge is being created, for instance, is used and benefits local communities. But that's really a very hard challenge to get that right.
Thank you. Adrian.
Wouter, thank you so much for your talk. It's very enlightening and great to see all that you've been achieving over these last few years. You talked about interventions, and of course the biggest intervention we're doing as a society is changing the physical and chemical properties of our atmosphere, and hence the energy balance and the hydrological response of the planet. You've been studying these high-altitude catchments where, of course, glaciers are retreating and snow melt, that key runoff from snow melt is also changing. I'm just wondering, how concerned are you for these catchments as you start to lose those cryogenic processes in terms of the impacts that it will have on those communities that you've been helping?
Yeah, that's a great question, and indeed one that gets a lot of attention. I would almost want to push back a bit in the sense that obviously, undoubtedly, climate change will have a main impact, but it's one amongst many other pressures on those systems as well. And while, for instance, cryosphere melt will have a local impact, the further you go, in a way, that signal dilutes, and at some point will become insignificant, and actually other types of impacts will dominate. And obviously, which of those is most important in a certain location really depends on the way that that the cryosphere signal mixes with, for instance, groundwater, surface water from non-cryospheric sources, as well as the type of change you expect in the future. And I think that's really the critical aspect to try and get right, and the very reason that at the beginning I had this, we go here, here is this graph that shows for instance, the downstream distance of the relative contribution of different systems. You can see that meltwater is obviously very important at the top of the catchment, but then its relative significance will decrease while it mixes with other sources of water. And obviously that also is important to then understand in the way that climate change might, for instance, reduce or change this signal, but probably will also change other signals. Wetlands themselves are also very susceptible to, for instance, drying and irreversible degradation as a result of climate change. And so understanding those different impacts from climate change, but also other pressures like environmental degradation, water quality change, land use change, is important to really know what is the priority and what is the overall change that you can expect from a pressure like climate change. And I think that really is one of the key challenges to understand in these kind of environments.
Thank you. I think one last question, please. Your name and affiliation, please.
Thank you. Great talk, Wouter, like always. Stefan Krause, University of Birmingham. I'm wondering, the examples that you have given were very much optimizing water quantity, and in the definition of UN water that you have up here for water security, it's saying acceptable quantity and quality of water. Do you see a risk with some of the examples like the leaky dams and leaky canals that you have given, which are a little bit forcing a managed aquifer recharge, that we trade off water quantity for water quality? And is there something in there for your type of sensors and sensor networks to actually make sure that we are not losing the quality of water that really is essential, in particular when we think of groundwater and subsurface water resources as well?
Yeah, I can't agree more. It definitely is. Yeah, you definitely need to take into account both, and in certain conditions you might have a trade-off. Although I would expect, in the case of a lot of the nature-based solutions, in particular, that you'd often be able to capture both and create an improvement both in water quality and quantity. But yes, I focused on the quantity aspect because that's what we do in our group, but it definitely doesn't mean that quality isn't important. And I think it, again, shows the need for interdisciplinary approaches and bring the required expertise together to combine both. And water quality is definitely a very important factor on the minds of water resources managers, and one where arguably many of the processes and issues that I've touched upon, for instance, the lack of data, is arguably even worse, or in the case of water quality compared to water quantity. So yeah, it's definitely, and the water security includes both for good reason, and we should look at both in order to solve these problems. Yeah.
So I'm sure the conversation will continue, but we've worked ever so hard. And so please take a rest. Thank you very much. So the reason I didn't ask for a big round of applause is that I've now got the pleasure of inviting, actually, Professor Buytaert mentioned her name in the presentation, if you're being keen and you are following. So it's my pleasure to introduce to you and welcome our Director of the Center for Systems Engineering and Innovation, Dr. Anna Mejic, to pass a vote of thanks to Professor Buytaert. So Anna, welcome.
Thank you, Washington. Good evening, or as Wouter said, good morning or good afternoon for the people who are online. And thanks, Wouter, for giving me the opportunity to close this, I think, really beautiful evening. And when I was thinking about what I should say today as someone who knows Wouter quite well, I thought maybe the easiest way to do that is to think of 3 words that describe Wouter as a person, as a scientist, and as a leader. So I'm going to start with the first one. And the first one that I've chosen, Wouter, is generous. And I do say that as someone who knows Wouter for a very long time, since he came to Imperial as a postdoc. And Wouter first became my friend, and then my boss, which didn't last for too long. And then we became colleagues. So in some ways, it's a huge privilege to be here because I do feel that we kind of grew up together academically. So from that journey, I've seen Wouter as a person who is really selflessly sharing his time and knowledge and ideas. And that is manifested in many examples of Wouter giving the feedback to the proposals, sharing his PhD students, giving the opportunity for his younger colleagues to work very closely with him and even lead the proposals, which is very, very strange in an academic community for those who have been around for a while. Wouter also keeps the people together and brings the people together, and lots of us here in the room and online know each other because of Wouter, which is really important for bringing and having scientific communities and networks. So my first thanks, Wouter, is a very personal one from me and from all the people that you have been working with, and thank you for being very generous with we talk about the scarcity, very scarce resources in an academic, which is the time and ideas and knowledge. And then my second word for Wouter is inspirational, and something that Wouter maybe didn't mention tonight, but he's very often talking about the hydrology as an inclusive science. And what he means by that is that really the purpose of the science is not to do the science because of the science, but to do the science to create a real impact on the ground. And I think if anything, what we've seen tonight is that impact that he managed to already create, and the presentation that can include so many photos of the things happening on the ground. Wouter has forever changed our knowledge and understanding of the hydrology and human impacts in the Andes. We've seen that tonight, and not just in the Andes, but in all other countries in the world, including we've seen examples from India, from Nepal, and from Africa. And Wouter is also something that is very rare in engineering, is interdisciplinary researcher, and we've seen examples tonight around using the citizen science in the context of sustainable development. We have seen his great efforts in having the networks of the low-cost sensors to try to get more information around the hydrological modeling and monitoring. And then finally, I think coming to the impact, we've also seen a great effort of creating a network of the participatory monitoring, which is operational now for many years. And Washington mentioned at the beginning that Wouter this year received Henry Darcy Medal. I just want to say that this is the most prestigious medal that the hydrologists can get. So Wouter, my second thanks is from the whole hydrological community that you have been inspiring for many years now. And on a personal level, I'm really looking forward to celebrating the medal in Vienna in a couple of months' time. And then the final word for Wouter is the way I think about the Wouter as a leader, and I've chosen the word influential. And those who know Wouter really well, they will know that he is not the person who talks easily about his successes. But we all know that influence very often comes from leading by example. And those of you who will have the opportunity or had the opportunity to meet Wouter in his office, you would see lots of equipment that is lying around that is used for his low-cost sensors that he is still putting together on his own. But his very, very good technical skills do come with the ability to think strategically, to bring people together and create new avenues of research. And I'm very much looking forward, Wouter, to seeing where the research around the nature-based solutions in the water security will take us. In the room, we have our environmental water resources engineering section, and I think as a member of the section, Wouter, I'm really looking forward for you to shape future hydrology research and also education. And I think from the departmental and the college level, we have in Wouter someone who can shape and influence the research strategies, and particularly in the context of sustainable development and interdisciplinary research. So finally, I would just like all of you who are here and maybe even online to join me in the final round of applause, Wouter, for this beautiful evening, for the very inspiring lecture and everything you have done for the hydrological community. Thank you.